really excited that Ban Har Yeap, I said it right, yes, yep, is here with us this week. He's actually working with the elementary faculty 3 days, both planning with them. We're going through a lesson study process, and Jimena and I were fortunate enough to sit with him with all of the teams yesterday, so we get to do most of the learning. That's, I feel a bit selfish. He's actually with us because he worked with Jimena when she was in Cambodia, worked with her faculty for 3 years, and so we feel very fortunate that he's here. He's currently the principal of the Marshall Cavendish Institute in Singapore. It's a professional development institute for teachers. He's also the director of curriculum and professional development at Pathlight School in Singapore, and the director, academic director at Anglo Singapore International School in Thailand. I honestly don't know how he has time for all of that and to do consulting. He holds a PhD in mathematics education, an MA in Southeast Asian Studies, and a master's in education. So we want to welcome him and thank him for being here with us.
Thank you very much. Good morning. Good morning, parents. I'm pleased to be here. This week, I'm actually here to present at a conference for the Central and Eastern European Schools Association that's happening this week. And in fact, the school is hosting a pre-conference event this coming Thursday, and I'll be presenting a mathematics workshop for teachers attending the pre-conference. And we took this opportunity for me to work with the teachers in this school over the next 3 days for them to continue in their journey to make mathematics learning an inquiry-based process. This morning, I'm here to have a conversation with you, so please feel free to just raise questions or raise points as we go along. It's not going to be a lecture or anything like that. To share with you what we know, how mathematics learning can be a platform for young learners to acquire not just competencies, but also attitudes, mindsets, worldview that can hopefully make them an awesome young person. Because I think beyond getting good grades, as parents, I can understand that all of us want our kids to develop not just abilities in academic areas, but certain attitudes, certain mindsets that will put them in a good place so that they continue to be able to access opportunities. And mathematics is a dangerous subject in that it can either go in a positive direction or make students absolutely hate learning that subject when it is not taught the way it should be taught. I think most of us can understand that. Yeah? So this morning I'm sharing with you some things we know from research, from theories. The school would probably post up the video and all the slides anyway, and they're all available on my blog spot. Ban Har is my name, is my first name, and in Singapore, we put our last name in front. It's a bit strange, but some of you can understand that because you do the same as well. I will start by just sharing with you a little bit of things that probably you already know as parents, that the demands for skills in the workplace has been changing a lot. This bunch of economists, they have been studying how the demand for different skills in the industries have changed over the decades. And they collected the data as early as 1960s, and they are still continuing with this study. And this graph shows us a very clear trend that some skills, apparently these are all the 5 big skills that different industries look for. And from this graph, you can see that some skills were in demand once upon a time. But the value, people are no longer willing to pay so much money for those skills. So those are the graphs that you can see. The red graph that went up in the earlier years, in the 70s, and then has been coming down. Pretty low value now. And then the blue one, likewise, has been going down. The purple one has been low all these years, but getting lower and lower in demand. The purple skill is non-routine manual skills. It's a manual skill, but it's non-routine. For example, if you're familiar with Southeast Asia, we can get food anywhere. You just walk out to the streets, you can get food. Street hawkers, they have non-routine manual skills. Clearly, it's a manual skill, but it's non-routine because customers like ourselves in Southeast Asia, we make strange demands. I want 2 kinds of noodles, more of the thin one, less of the thick one, no bean sprouts, more chili, and all kinds of strange requests. It's clearly non-routine because, you know, customers like that. I mean, those are valuable skills. Unfortunately, it's very common. Almost anyone would have that kind of skill. And although it is a valuable skill, not many people are willing to pay good money for it because it's so common. So for example, for €2, you get a good meal from the street hawker in Southeast Asia. So that is the one that's a bit unfortunate, but understandably because of, you know, demand and supply. The red one and the blue ones are the ones that used to be quite valuable, but no longer as valuable as they should. And economists are predicting that some of this will become valueless in the near future. What are they? One of them is the blue one, routine manual. We can understand why. Factory work, automation, machine learning, robotics have caused, you know, places like that, industries like this, not to want to employ human factory workers anymore. So these are routine but manual factory work, for example. The other one is routine cognitive. In other words, it requires thinking. It's cognitive. So doing mathematics is cognitive. And if we don't learn mathematics properly, it can be routine cognitive. So when we do mathematics in a routine way, in a procedural way, here's a rule, just follow it. That's really routine cognitive. So mathematics is a dangerous subject in that way. If not learned carefully, it can make you cultivate a skill that is really valueless. The 2 skills that are becoming more and more valuable, what is common between them is the fact that they are non-routine in nature. The one in green is non-routine interactive, and the one in yellow is non-routine analytic. So when students, when young people are able to do non-routine things, and couple that with ability to analyze, break things down into manageable bits, handle it, and then put it back again, that will put them in a good place in terms of, you know, what people are willing to pay money for. The other one is non-routine interactive, which is a skill needed to solve a problem that changes even as you are solving the problem. So unlike school textbook problem, when you solve the problem will stay the same throughout the solution process. But when you are using non-routine interactive skills, you are able to handle problems that changes even as you are solving it. Many of us know that a lot of workplace problems today are like that, and machines and despite their cleverness in machine learning and artificial intelligence, are still not as good as humans in handling situations like that. So that's just a bit of economics. So I think schools like ISP have visions and mission to cultivate young people so that they have a set of skills that are, you know, in demand and continue to put them in a spot that they can have whatever opportunities they wish. I come from Singapore. Many of you know it's a small country, 5.5 million people, a very small space, no natural resources. We buy water from Malaysia. We buy sand from Cambodia and Indonesia. Have you heard of countries that buy water and sand? Now you have. It's called Singapore. We have nothing really, nothing that's natural except for human resources. Say again?
You're not buying air like China.
We don't buy air, but we get air from Indonesia. We know that for sure because every year when they slash and burn, we get the pollution, and we know it comes from Indonesia. So even the air is not ours, really. We don't need to buy them, we get them for free, but it comes with the yearly problem that we get during the slash and burn season. Anyway, in Singapore, we suffer the same fate as Southeast Asian countries, as in we did not do well in educating our young people. So on the international ruler, 500 is adequate. So East Asian countries like South Korea, Japan, Hong Kong, they often do a lot better, as in their students are around 550. 40 points is 1 year of learning. So 550 is about 50 points above 500. So 500 is adequate. 40 points is 1 year of learning. Whereas in Southeast Asia, like in Thailand, the Philippines, Malaysia, Indonesia, and early years, Singapore, we often launch around 450, which is 1 year behind expected level of learning. And that was the impetus for Singapore government to do something about it. And over the years, I've been traveling everywhere to share with educators around the world some of the experiences that we have in turning the situation around. And today in Singapore, mathematics learning is done in what we call a problem-solving approach. And I'm sharing some of those with you. So I think some of you might know this rather famous economist. Back in the 80s, he produced a book, Mind Over Matter, which essentially talk about how countries that used to be rich because they are rich in natural resources are no longer rich countries. Countries that are going to be richer and richer in the near future are those that have intellectual capital. So mind over matter. Natural resources, matter, will no longer be the determinant of wealth for nations, but mind, intellectual capital, how well our young people are educated will be the critical determinant in how wealthy nations are going to be. This book was done like in 1980s, but over the years, it's increasingly shown to be, the thesis is shown to be true. Yeah. So what I'll be doing with you this morning is to share with you using some examples, maybe like subtraction or long division or word problems to talk about mathematics learning, how when well learned, it can help our kids to become a better thinker, a better person. But when not well learned, it can cause problem in their whole mindset about their ability to learn and their whole worldview about things which are mathematical, technological. Yeah. Anyway, that's the brain, rather an image of the brain. And those are the different parts that are responsible for different things, often referred to as mathematics. That's the front of our head, and that's at the back. So this part of the brain at the back is responsible for visualization. Visualization is the ability to see more than what our eyes can see. In other words, it's really critical to understand anything that we cannot see using our eyes. In other words, abstract things. And because mathematics is inherently abstract, that part of the brain is obviously critical in doing mathematics. When you memorize, that part of the brain is used. When you memorize a lot, that part of the brain becomes well developed. When you do a lot of calculation, as in the procedural way on paper, for example, then that part of the brain will be used, that part of the brain will be developed if you do a lot of those kind of things. The simple thing about brain is that when you do a lot of things connected to those, then that part will be used a lot, and hence that part will grow and develop. The frontal lobe, the front portion of the brain, as you can see, does quite a lot of things connected to high-level mathematics work. Example, problem solving. Example, forming concept. When students can understand a difficult concept, that part of the brain is needed. So that part of the brain needs to be highly developed in order for a student to be able to grasp concept. Metacognition is our brain's manager. So the brain has many workers. The brain is busy doing things. But metacognition is the boss. Metacognition is the manager. Unless our metacognition is highly developed, we cannot manage multi-step thinking. We get confused easily when things become complex. So metacognition is quite an important skill to have when students are dealing with things which are complex, things which are multi-step. Example, when they're solving a fairly difficult maths problem, that ability is probably critical. Reasoning in an abstract way, which is clearly needed in mathematics, and mental flexibility. Some people say creativity. That's also the frontal lobe of the human brain. So as you can see, different parts of the brain does different things. Not sure about you, when I went to elementary school, primary school back in the early 70s, mathematics is presented as a lot of computation. So we did a lot of crazy kind of tedious computation, like multiplying 5-digit numbers by 3-digit numbers. Just a waste of time, really. But we were subjected to that kind of learning. When we do a lot of that, that portion of the brain will develop. And then our teachers expected us to memorize this and memorize that. We have to memorize practically everything. And that portion of the brain is engaged, that portion of the brain is well developed, which is fine. Except that when we need to visualize, we cannot do it too well, because our mathematics learning has been dominated by calculation and memorization. So the parts of the brain that got developed are not the parts of the brain that we need to do more difficult things, which is that part and this part. So this morning, I'm going to share with you some things we know from research, how mathematics can be learned in a way that can enhance the critical portions of the brain. I'll do one example with you, and then I'll pause to take some question. Let's take something that is commonplace. Let's say subtraction. Let's do something maybe from, I don't know, grade 3 maybe, when they need to do subtraction like this. And I think because we all come from different countries, probably the way we learned it might be slightly different from countries to countries, but the ideas are essentially the same. So many of us might remember going to school and doing a bunch of things that require us to do something to this effect. And then I'm not sure we did, but I'm sure we canceled something away. And then something happened. I'm not sure what happened, but what I'm trying to say is that the mathematics that you and I learn is still the same mathematics that children learn. Maybe what might be different is the way they are learning it. Most of us probably learn this in some kind of procedure. The teacher may say things like, you go to the next door neighbor, it's not enough, so you go to the next door neighbor, you borrow something. So let's see how is this learned in a way that it benefits young children. So you probably know your children come to a school that's highly well-resourced. You know, if our teachers in Singapore see your rooms, I think they will all come and teach here. In Singapore, we are 100% state school system. There's no opportunity for private schooling for citizens. So if you are Singaporean, you can be as wealthy as you are, you just need to suffer with everyone else in the public school. So there's no provision for private schooling. Anyway, so, but in Singapore or in this school or anywhere else, teachers have been trained to teach children mathematics in a certain way. That's according to theory. And what they would do are things like that. They would represent numbers using images like that. Nowadays with app, you can use apps like that, but they also have the actual toys, the actual manipulatives, we call them, the actual apparatus, things that you can use to make sense of whatever that you are learning. So this would be 300, because each of these would represent 1. And actually, there are like 100 of it, making up the red piece. So that's what they would do. They would represent a number this way. My rubbish bin is not working very well. So that's 300. So if this is like 300 euro, and you want to spend 125 euro, so if you're interested to do something like that, then spending the 100 euro is not a big deal because you do have 3 red things. So you need to give away 1 red thing, 2 blue things, oh, I don't have them, and 5 yellow things. Oh, we don't have them yet. So the children are probably asked to go and work among themselves with the concrete materials, help each other, figure it out. How should we deal with this problem when we have 300 children and 125 of them went on a field trip? Or whatever other stories the teachers choose to use to help them understand what they are doing. So the critical part of learning is students using concrete materials, students working somewhat independently on their own, among themselves, students helping each other. Sometimes they have the right idea, sometimes they don't. Sometimes what they hear the friends say they agree with, other times they don't. But they will spend time exploring. And at some point, during the discussion, they will say whatever they say. Among other things, some kids will say things like, since you need to give away one of this, that's not a problem at all. It's there already, just give this away. But the problem is that you need to give away 20, 2 tens. We don't have it, but thankfully, we can kind of get this to become a bunch of tens. Oh, now giving away the 2 blue things, the 2 tens, is not a problem anymore. But I also need to give away the 5 yellow things, 5 ones, which I don't have, but not a problem because I can easily get a bunch. And here we can see that 300 can also be perceived as 200, 90, and 10. That's mental flexibility. You do not look at 300 as just 300. You are also able to see that 300 can also be called, can also have the name of 200, 9 tens, and 10 ones. And that is what children do. So what we have here, what you and I learned when we were young, our teacher asked us to write it this way. And that's what we have just done. Currently, it is 300. But for the purpose of today's problem, it's better not to look at it as 300. It's better to look at it as 200, 9 tens, and 10 ones. Mirroring what we just did with those pieces a while ago. And that is it. It's as simple as that. No stories, no borrowing. Just the simple idea of being able to see 300 in a different way. And once we see 300 this way, giving away the 100 is easy. 2 red ones, give away 1, you're left with 1. 9 of those blue pieces, you give away 2 blue ones, of course it's 7. And then 10 ones, 10 of those yellow pieces, you give away 5, you have 5. And you put it all together, and you get your final answer. That's it. It's straightforward, it's simple. Not sure about you, when I went to school a long time ago, our teachers, not their fault, they were trained differently, overcomplicate things by giving us some stories, some stats, some procedures. But it's actually as simple as that. And this idea is applicable in other calculation. For example, when you need to do a calculation like 351, using the English notation, or using the European notation, or using the Swedish notation. These are all the different notation people around the world use to do dividing. So if we have this amount and we share among 3, however you write it, This is not very difficult, because if we have 351, so that's 300, and 300 share among 3, that's probably the easiest bit. But problem would be maybe the 51, because 5 share among 3 is a little bit inconvenient, and 1 share among 3 is also inconvenient. Again, the children are given the problem, time, friends, equipment, and on their own, without the teacher telling them, boys and girls, listen to me first. You wouldn't know how to do it until I tell you. Listen carefully. That's not the way of learning. The way of learning is give them time, give them space, give them friends, give them equipment, and give them the faith that they can figure it out to a certain level. And tell them that, okay, how would you put this equally into 3 boxes? And give them time. I'm sure they will say something along the line, oh, those 3 red ones are easy, 1 for each box. But the blue ones, oh, we got so many. But 3 of them, if I had 3 of them, it's easy. So this lot is a bit troublesome. Oh, but I noticed there are actually 21. And 21 put into 3, not so difficult. If I know my times table, that will be 7 in each box. And that's it. When you divide 351 by 3, you get 100 from here, 10 from here, and 7 from here. 117. That's it. It's quite straightforward when students are doing that. In both examples, I have done the exact same thing that children who are highly able in mathematics tend to do. They are very capable of looking at numbers in multiple ways. For example, for the purpose of subtracting 125, they saw it as 200, 90, and 10, because that facilitated whatever they wanted to do, which is to subtract 125. In the case of 351 divided by 3, they look at it as 300, 30, and 21, because that will facilitate whatever they want to do. Different countries write long division differently. If I use the American, British way of writing, they tend to write it like that. And what they do is they would first take out 300, which is what the kids did with the equipment. And as a result, they are left with 51. And then they take out 30, because quite easy to put 30 into 3 groups. And then they are left with 21. And 21, I suppose, is manageable, so they take it all out. That means everything is accounted for, and nothing is left over. And from here, they got the 100. From here, they got 10. From here, they got 7, as I described it earlier. And that's it. But I'm not sure how you learned it in school, but when I went to school, it wasn't taught like that. It was quite complicated. I will spare you the complication, but you probably would understand what I mean by the teachers back in those days tend to give us some procedures, some steps that we tend to follow, right? So when students learn mathematics in this way, breaking numbers apart, that will be one way to enhance their ability in higher level of learning when they move to middle school and high school, right? So that's the first thing. Breaking numbers apart. So if you are helping your children at home, some of you do that. Although, in school they would have done adequate job already, but some of you do kind of help your kids with homework. One of the things you can help them with is this, breaking numbers apart. That will cultivate the frontal lobe of the human brain, which is required for quite a lot of high-level thinking. So if you ask me a simple question, how to make sure my kid will become quite good in high-level mathematics beyond elementary, this will be one big answer. develop their number sense. What do you mean by developing their number sense? This is it. Help them break numbers apart appropriately. Right? I'll take questions. Something that you would like to bring up. Feel free to chat. You don't have to be quiet, you know. This is a maths class. We cannot learn maths by keeping quiet. When you go to a class and it's quiet, it's probably suspicious. Anyway, so yeah, any question you would like to ask, anything at all, I'll be happy. Yes, please.
There must be something to what you're saying, because if I remember, Singapore is one of the top countries in the world in terms of mathematical skills.
Today, yes.
Is that right? Today,
yes.
Yeah. One of the things I wonder about, but I went to school before you were even born, so
I'm quite old.
it's quite ancient way of learning. Although I've had a lot of abstract mathematics in my life. The one thing I think about is the word balance. And I think this is probably absolutely the way to go. However, it seems to me that there's some things that come from yesteryear, like learning the times tables, for example, which I think is really important, because when my daughter goes to Albert's down the street to buy a loaf of bread and she gives them 100 crowns, she's not going to have time to do this on a piece of paper. Yeah. So I wanted to get your perspective about the balance between some of the old calculating stuff and the new abstract way of thinking.
I'll answer that shortly. There are other questions? Yes, please.
Manipulatives. I mean, I saw the pictures, the block pictures, as a manipulative, like a Montessori. Yeah, that to me is a powerful way of thinking, and using our hands as the way to get them to their minds exercised in that part. But what do you think of manipulatives? How does that fit?
It is a critical way of learning anything, not just mathematics. It's based on a well-known established learning theories from the 60s, that anything abstract, you must begin through a concrete experience. So it is important. And hence the importance of play-based learning, especially when they are very young, because it's through the psychomotor movement that our brain get developed. So without the movements through objects, manipulative, our brain don't really get developed as well as it should, isn't it? So it is important. And it is not just an opinion, it is a well-established learning theories that anything abstract is best learned through concrete experiences. Yeah? Anything else before times table? Yes.
Just about mathematics is a very big word. I mean,
yes.
It's infinity. It's very, very broad. I don't know where to start it if at all. And my question, you were referring to it as elementary level calculations or mathematics, I'm not sure. Do you think that kids in early school should be introduced to mathematical concepts such as infinity, the idea that between 0 and 1 there's an endless number of numbers, minus? What do you think? Because
I think just like all concepts, young children will learn the first layer of it. When children learn about our human body, they don't learn things like blood vessels, plasma, cytoplasm in a cell. They don't learn all that. DNA, they don't. They learn, oh, I have 2 eyes. I have a nose. And then later they go into details of it. Likewise, mathematical concepts. So I think when they first learn something, they will not learn everything about it. Some children are able, because of their interest, to find out more. But in a typical way of learning, we probably will learn about whole numbers first before we learn about fraction. And then at some point we realize, oh, that means between 0 and 1, there are so many numbers. And that might happen only in grade 4. So I think when they first learn something, they tend to learn the big picture about it. So if you're talking about young children, I think they usually learn 3 things. So in early learning of mathematics, they learn to count, to appreciate numbers, and flexibility in breaking numbers up. So they will do things like, and that will bring me to times table. They'll do things like, oh, I can show you the number 5. And they got toys like that, manipulative like this. And they'll say, oh, that's 5. And 5 is 3 and 2. But 5 is also 4 and 1. It's also 1 and 4. It's also 5 and 0. So that's one thing they learn when they are very young. They are rather playful with numbers, as in they represent them, they break them apart. The other things that is important when children are young are images, visuals, so shapes. And the third thing that's important are comparison. Oh, this snake, toy snake is longer than the other one. Oh, this doll is heavier than the other one. This box is bigger than the other one. I'm smaller than this box because I just went into the box. So things like that. So these are the only 3 things. I think early learning, the numeracy part is not that critical. Young children need to learn to explore. They need to learn to play. They need to learn to get along with other people. And they need to learn language. So if you ask this person who is called the father of kindergarten, he will say basically that young learners need 2 things, socialization and language skills. Numbers can happen a little bit. And you're going to acquire a bunch of numerical things anyway, just being a child, playing, interacting with other adults. Yeah, anyway, so those are some things. They don't need to learn everything just yet. Coming back to times table, multiplication facts. Just like everything else, like languages, if we cannot do basic things, we cannot do higher level things. If I struggle with basic grammar, I cannot write a spectacular essay. No way. If I cannot spell basic words, I cannot write a proper email. So I think we all understand that basics are important. So in mathematics, there are some basics. Many of us would think multiplication facts as a basic. If you do not know what is 3 multiplied 4 times, then it's very difficult for us to do anything higher, anything more spectacular. So I think it's a given that basic skills, some of us say the traditional stuff, are important. I think the 2 things I did with you are traditional stuff. You and I learn how to subtract. You and I learn how to divide. Nothing wrong with this. These are important. Although today we have calculator. But it continues to be important because it trains our mind to see numbers in multiple ways. So these are basic things that you and I learn. Our children continue to learn them. What is different is the way of learning them. Similarly with multiplication. So we probably need to know facts like that. The question is, how do we learn the facts? Research and theory say that we do not learn it because we memorize it. Memorize as in rote memorization. Sit there and just chant. 9 times 8 is whatever. Like 3 times 4, 12, 3 times 4, 12, or whatever we do. You know, the chanting or whatever, rote memorization. Human brain can remember without the need to memorize. All of us know that. When your children or child was born, did you and your spouse write down his name and say, spouse, let's memorize our kid's name because we need to remember his name. He's Nicholas. Okay, let's put it behind. Don't look at it. Say it 5 times. Nicholas, 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 Nicholas. Spouse, let me test you. Do you still remember? I'm sure you didn't do that. But yet you remember his name. So it's quite established that we all can remember without having to memorize. Same for this. We can remember this the way you remembered your children's name. It wasn't much of an effort. It wasn't much of a difficulty. We can remember this. In fact, research tells us that we cannot remember because we memorize like a parrot. Rote memorization is one surest way for kids to not be able to learn things properly. They might remember it for a while, and through sheer rehearsal, maybe they will remember it. But it's not going to help them in the long run, because when you do a lot of memorizing, you probably already know which part of the brain got developed. This portion of the brain got developed, which is okay. But if you want that same child to be good in problem solving, forget it. If you want that same child to be spectacular in geometry in high school, forget it. So memorization does serve the short-term need, but it doesn't help in the long run because it's building a part of the brain that is actually not needed for anything else except to remember, as far as mathematics is concerned. Worse, the memorization is not enjoyable to that child, or in some cases traumatic, because they get some kind of scolding when they are not able to remember it. So if that process is not pleasant, then it adds on to the mindset of the child. The third thing that memorizing is not good for the child is the fact that they grow up thinking that mathematics is memorizing. Mathematics is not memorizing. Research by the mindset researchers like Carol Dweck has informed us that kids who see mathematics as memorizing, following steps, do a lot worse than kids who see mathematics as figuring things out. And that's what we want our young people to be. That they think that mathematics is just figuring things out. When we first learn multiplication facts, the teacher wouldn't say, okay, all of us, today we are going to memorize the 8 times table. Sit down and let's chant the 8 times table. No teacher today in his right mind would do such a thing. The teacher would say something to the effect that, you know, we have a friend, he's spiky. I wonder why he's still smiling, because he doesn't know this. But it's okay. Not knowing is no big deal, as long as you can figure it out in a short amount of time. Let us now work with our friends. We have the equipment, and let's try to see what advice we can give Spiky. If he doesn't know, what can he do to figure out the value of 9 rows of 8? And when they first learn multiplication tables, they would have learned things like, this is 1 row of 8. This is 2 rows of 8. So they represent abstract expressions like 2 times 8 as 2 rows of 8, 2 groups of 8. So they know that this is 2 times 8. That means they got a mental image of what is 9 rows of 8. And different kids will share different things eventually. So remember, how do they learn anything? Give them time, give them space, give them friends, give them the concrete objects, and give them the faith that they can figure things out. And they often can, up to a certain level, sometimes completely. And when we teach this lesson to many, many children over the years, in hundreds of classrooms, we will always hear some of these things. A very common one would say, oh, we would advise Spiky and ask him, does he know 10 rows of 8? Because a lot of people, even our group members, everyone, even he who is not able to remember everything, even my friend knows what is 10 rows of 8. And we would advise Spiky, if you know 10 rows of 8 and you need to know 9 rows, just remove 1 row of 8. Oh, so 80, remove 8, 72. In a short amount of time, even though Spiky doesn't know, he can figure it out. And another group may say things like, oh, actually, we have another way, because if Spiky knows 5 rows of 8, and a lot of people tend to be able to do that, then all he needs is to know 4 rows of 8. If he knows 5 rows of 8, he knows 4 rows of 8, then the problem is solved. Okay, maybe Spiky cannot remember 4 rows of 8. Then we advise him to just start from 2 rows of 8. Once you know 2 rows, you double it. and then you figure out whatever you need to figure out. That's our advice to him. So that's how young learners learn things like times table. They learn it by figuring it out. The figuring out process is important. The figuring out process, this one, is like putting hooks in the room. If you try to hang the coat without the hook, without the hooks, you can try as many times as you want. The coat will not stay. You try to put it on the wall, it drops to the floor. So it is important, in order for the facts to stay, in order for the codes to stay, we must first help our kids build the hooks for retention. Rote memorization doesn't build the hooks, because rote memorization is a low-level mental process. Low-level mental processes contribute very little to brain growth, whereas things which are slightly harder grows the brain. We all know that for the brain to grow, some kind of struggle is necessary. If everything is smooth sailing and easy, although we can do it, our physical brain doesn't actually grow. So that's how things like times table is taught. And over time, you figure it out, you figure it out, you figure it out. At some point, you will just remember it. So the remembering is just a product of learning to figure out. And that's basically the neuroscience behind remembering. We remembered things like that because we spend time figuring it out. And then there's a point of departure that the kids will just remember it. And sometimes they forget. Then they can just trace the step and get to it. Yeah? So yes, very important. Things like times table, they must know it. But it's not learning by chanting, singing a song, memorizing like a parrot. Something else you would like to bring up? Yes, please.
I sometimes question, or I sometimes think that the calculators sometimes destroy our way of thinking here.
Yes.
When I studied engineering 150 years ago, calculators didn't exist. We used slide rulers.
Yes, I did that too.
I think that's a right English word, but most of you don't know what a slide ruler is. And that gave you that sense you have described for us today.
Yeah. And that is it. But there is a place for calculator. I think when computation are tedious, and sometimes in real world, you get decimals and you need to, compute with those 3 decimal places or 2 decimal places, I suppose you would just use a calculator. So I think the basic role of doing computation in the modern world is like that. When the computation is friendly, you will do it in your head. 51 divided by 3. Oh, 30 and 21. 30 gets me 10. 21 gets me 7. 10 and 7, 17. That's what you will do. 29 plus 74. Move 1 over. 30 and 73. 30 and 70, 103. So anything that's friendly to the human brain, we would do it mentally. So mental calculation is the pinnacle of doing arithmetic. But young children are not very strong in metacognition, which is needed in what I just did. When I am doing things like 52 divided by 4, I need to break it up into 40. I put the 40 away. Then I go and figure out the other number, 40, 12. Put the 12 away. Go and look for the 40 to put into 4. 10. Put the answer away. Go and get the 12 back to put into 4. 3. Put it away. Go and look for the quotient, 10. Look for the... So as you can see, the brain is doing a fair bit of mental gymnastics. In order for the brain to be able to manage that, metacognition must be very strong. Young children do not have very strong metacognition yet, so they are writing it down as a temporary thing. So the writing down is really a bridge to not have to write down. So doing arithmetic, the pinnacle is always mental strategies. In between, we write it down. But when the numbers are not friendly or repetitive, we will just use technology, like a calculator. So there is a place for calculator, but obviously if people use calculator indiscriminately, then They are not training their brain to do things like what we just described, which is quite important, metacognitive things. Something else? Yes, please.
Well, the way you talk about metacognition, I'm thinking, well, you need time for that. What secrets do you have for keeping yourself from saying, I know it, I'm about to teach to you?
I think my colleagues in this room who have seen me teach, they can describe to you how patient as a teacher I am, or how stubborn as a teacher I am in not giving away the answer. So whenever we teach students, we must never, whenever we teach our own kids, we must never get into I know it all kind of mode. So it's never teaching the kids. It's never solving problem for the kids. It's always solving the problem with them. So our role is not to explain things to them. Our role is to provoke them into imagining the next thing that. So I have no secrets for you, but as a teacher, that's what we are trained to do. We are trained to scaffold. We are not trained to explain things. So I will not be able to, I know the answer, I explain it to you, because that's not the way we are trained to do it. So it's just scaffolding. Let me demonstrate scaffolding using a word problem. So all right, let's take a look at a word problem. I'm going to write the word problem. I wonder if you can guess what the next word is. The first word you don't have to guess is a usual suspect. It's spiky. Can you guess the word? Can you guess the next 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 word? Another word for it? Could be either one. Could also be this. It's the same word. Can you guess the next word? Can you guess the next word? Can you guess the next word? Are you a mind reader? Can you guess the next word? Are you a mind reader? Selfish fella. Spiky spent some of his savings on a present and some of the remaining money on a toy for himself. As you can tell, it's a fairly complex problem that some adults are fearful of because you see fractions. But are you able to imagine if I draw a diagram to represent his savings? Do we know how much his savings was?
See, for me, it would be immediately algebra. Like, I would immediately say his savings are x.
Sure.
And what he has left is 4/5
Sure.
of x. And then 4/5 of x times 3/4. See?
Which is valid, this is valid, except that typically at elementary level, they are not going to have that technical skill yet. But yes, those of us who know algebra would start with let the savings be x. The young kids would let the savings be x, except their x is a pictorial x. This is a pictorial x. This is x. So they are going to say that, oh, that's a savings. We do not know it. So that's the unknown. That's the x. Are you able to see which part of the diagram stands for how much the present costs? Are you able to see? Are you able to draw it and show me which part of the diagram he spent on the present? I'm going to now draw the diagram to show how much the present was. Can you imagine? Can you imagine what I'm going to do? Were you guessing that I was going to do something like that? I'm going to now shade the diagram to show which part of the diagram show how much the present costs. Can you guess which part of the diagram I'm going to shade? Were you guessing that? No, I'm just fooling you. But can I do that? Of course I can do that. But I rather do this. I wonder why. Is there a reason why I rather do that? Although both are correct. I'm not sure. I'll leave it to you to think. So that's how much the present costs. Maybe it's good to kind of just remind ourselves and let our audience know that that's for the present. Are you able to see the remaining money? Are you able to see how much he spent on the toy? Are you able to see 3/4, 3/4 of the remaining money? Is it something that's quite easy to see? Do you think a lot of people can see it? Oh, I'm sorry, I gave you the wrong problem. My eyesight not very good. I read the wrong problem. It's actually not 3/4. It's actually 3/8. Are you able to see which part of the diagram he spent on the toy? Now that I gave you the right information. Parents, do you see as an adult helping children, we scaffold their learning. We don't explain to them. We do not solve the problem somewhere in hiding, consult our friends on the phone like, oh, how do you solve this difficult problem? Have the solution and ready to show off how we solve the problem. Children learning maths is not a spectator sport. They don't need to watch us solve the problem. They don't need us to explain to them how to do it. They need to learn how to do it for themselves. When they find something difficult, the way they learn is through the little scaffolds. And in my little demonstration, I demonstrated how a teacher, an adult, can scaffold young learners' learning. So you'll notice that I'm not too eager to just show you. I will ask you to, can you imagine? Can you see? Can you picture in your head? And I did not even do it for you.
And that's something that you did on purpose, right? You put the 4 there
yes.
because it's easier. They would see that first
That's
and
right.
then move to the...
So you're preparing the brain to do difficult things. Sometimes as adults, we are so fearful that our kids will crumble. Their self-esteem will be damaged forever just because they cannot do a difficult problem. Rest assured, human spirit is more resilient than that. No maths problem can damage our self-esteem. There are many other things that can do that, but not a maths problem. Anyway, the reason why young people can do difficult things is because their mind are ready. And that was just a little demonstration how we prepare their mind for something that is a little bit more difficult. So 3/4, 3/8. If I want to torture you somewhat, I'll give you 3/7. But I will not do that in the morning. I will do that with my students. But anyway, once you have this 3/8 and you can imagine, and I think at least one of you was saying maybe you want to do that because it's much easier to see 3/8 now.
And what if they cannot?
What if they cannot?
Because for us it's easy, we just get it. But for them, what if they cannot because they are not prepared yet or whatever, or something more complicated?
Right, obviously this will not be the first problem they get in the unit. And earlier in the unit, they would get probably problem like the first part. Spiky spent 1/5 of his savings on, that's it. And then we slowly build them. So the reason why some children cannot is because their path to the difficult problem is not well planned. So you notice how we plan the path for them. Even for this problem, I show you how we start from 3/4 to 3/8. What if they cannot see it using the diagram? The answer is always the same. When students cannot benefit from diagram, you always go back to concrete. That's from the Brunner's theory. We learn everything abstract by starting with the C, the concrete, then move on to the P, pictorial, finally getting to the A, abstract. Teachers refer to this as the CPA approach. The answer is always there. When students cannot see something abstractly, we move to pictorial. When they cannot benefit from the diagrams, we move back to the concrete. So that might be folding and cutting or whatever. Yeah? Similarly, if they cannot see something, then my questioning might be closer. I may ask more close questions to lead them through the small steps. So you can see from here that I didn't even give you a question, but if I ask you things like, do you think you can find out his savings? Do you think you can find out how much a toy costs? Do you think you can find out how much a present costs? The kid will say, not enough information. Can you request for one piece of information? And if it's available, I'll give it to you. And they may say, oh, do you know how much money he has left? Say, oh, as a result, he had $60 left. If you know that, do you think you can figure out all the questions we ask? So if we know that after spending money on the toy and on the present, if Spikey had $60 left, are you able to see where on the diagram the $60 is? So when your children cannot see it, you always go back to concrete. You may ask a different question. You do not explain to them. You do not explain to them one more time, but slower. You do not explain to them one more time, but louder. You always go back to concrete, or you ask a smaller question. Anyway, if the kids can see it, then they can see that, oh, that portion is a $60. If that's all the $60, that's really 5 bits. Then a simple calculation tells us that 1 bit is $12. And that tells us that the present, which is 2 bits, is $24. And the toy, that's 3 bits, is $36, and so on and so forth. As you can see, this is algebra, but this is done around grade 5 as well, and they use a pictorial representation. So this problem in itself is not very important, but it is important that kids get this problem to have the opportunity to use diagrams. That's the second answer. How to make your child ready for high-level mathematics. Earlier I talked about number sense, breaking numbers apart. Now I share with you a second big answer. Extensive use of diagrams. Even when they go to middle school, high school, and they do things like algebra, simple algebra in middle school, 1 less than twice an unknown number equals to 9. You know, simple linear algebra. Of course, at some point, they're going to do it without having to draw anything, without having to use concrete materials. But when they first learn it, I can imagine they're going to draw diagrams like, oh, that's the unknown number. I don't quite know how much it is, but that's the unknown number. But I got twice of that number. So just draw another portion. And I know that 1 less, I don't quite know how much is 1. Let me just assume this is 1. I know that 1 less than twice the unknown number. I know that that is really 9. Parents, can you see now how clear it is what the value of 2x is? So from the diagram, they can see that 2x is really just, what else can it be? Almost no need for any kind of interference from any adult. It's as clear as day that twice the unknown number is. But without a diagram, the teacher may have to resort to what you and I might be familiar with. Boys and girls, -1, when you move it to the right-hand side, the negative becomes positive. Why? That's the way it is. When number crosses the bridge, it changes the sign. That's the way it is. But why the need for that? You don't even need a rule. Because from the diagram, it's so obvious why it's 10. So you see, when we do not have visual representation, we need to rely on strange rules just to get the same numerical value. But otherwise, it's so easy. Like here, if 2 lots is 10, then what else can it be? 1 lot is 5. That's it. No need for artificial procedures like 2x equals to 10. Now, when 2 go, it goes below. Then the kid will ask, how come that one changes sign, this one goes below? And then like, oh, that's the way it is. Like, you know? But it's really not necessary.
When I explain this to my daughter, I tell her you want to get the x on one side and all the numbers on the other. So you're going to start by adding 1 here and adding 1 to the other side to keep it equal. And then dividing 2 here and then dividing 2 here to keep it equal. So,
which is a valid explanation. But as you can see, you don't even need the explanation because it is clear from the visual. So it is a visual that makes us understand lots and lots of difficult things. I suppose the saying, a picture paints 1,000 words, is exactly that. You'll notice that I didn't say 2x minus 1 equals 9. That's pointless. That's just noise. Nobody speaks like that. 2x minus 1 equals to 9. What I said was 1 less than twice an unknown number, which is reading the sentence. And that's what our friend is saying here. It is important for students to be able to read mathematical sentences. If they look at this as 2x minus 1 equals to 9, that means they are not understanding it. Unless they can say it maybe, oh, it's 1 less than twice a number. Same with this. 51, whatever, share among 3 friends. It's reading it. 9 flowers in 1 container, together with 3 more in another. Reading it. 300 children. 125 of them left for a field trip. I have 300 euros. I spent 125 of it. That is the third thing. Mathematics is a language. If you want your children to be able to perform at a fairly spectacular level when they are older, make sure they are not illiterate in the mathematical language. Many children are illiterate in the mathematical language because they do not hear how this is being read. As a result, they cannot read it. All they can do is to say what they see, 2x minus 1. But when they can read it, things which are quite complex become sensible. Just like any languages. Like I cannot read the local language. Even a simple sentence, I cannot figure it out. Not because I'm not of average intelligence, but because I'm illiterate in the Czech language. Right? So it's the same in mathematics. Mathematics is not spectacularly difficult, but it can be the moment we cannot read the language. And many kids cannot read the language for a variety of reasons. So they look at this, they have no idea. They have no idea how to make sense of things like what we are looking at here. They have no idea how to make sense of things like that. Because they will just like mumble like 3x minus 1 over 2 minus 1 equals to 9. If I say it like that, I'm just making noise. It doesn't mean anything to me. My brain cannot interpret it. But if I say that, oh, 1 less than a fraction, 1 less than that number is 9. 1 less than that number is 9. I wonder if I can figure out what that number is. 1 less than it is 9. Oh, of course, it has to be 10. It's just like that. But I need to be able to read it. Right? That's a third thing that you can help your own kids with. Ensure that they know how to read mathematical language. Not 9 plus 2, but 9 and 2. 9 flowers together with 2 flowers. 9 sweets that I have and the 2 sweets that you have. Just make sense of it. Oh, I have a number. When the number is divided by 2, when the number is halved, I get 10. I wonder if I know what that number is. Do you think we can figure out what that number is? If halving it gives us 10, it's clear. You see, mathematics is not difficult the moment we are literate in the language. And we continue from there. Oh, 1 less than that number is 20. Oh, that number got to be 21. Just like that. No artificial rules. 3/4 of a cake is left after a party. Not very delicious, probably. But 2 friends do not like to see it go to waste. So they share it equally between 2 of them. 3/4 of cake shared equally between 2 persons. That's the same as to say each of them gets half of whatever they are sharing. That's what our friend's saying. The audio that goes with it. This is a well-known procedure you and I learned. When we went to school, our teacher would say things like, when you divide a fraction, that's something special. First, you change the divide to multiply. That's the way it is for fraction. And because 2 is a whole number, you stick this in. And you need to stick this in because you need to invert it. And then after inverting it, you multiply the numerator. 3 times 1 is 3, 4 times, and all that. Why is there a need for that procedure? You must remember to change divide to multiply. When actual fact, getting it is so obvious, isn't it? So this morning I share with you, in a short amount of time, the top 3 things that we as adults can do. There are many other things, but if you get these 3 things in place, it covers most of it. First one is number sense. Second one is the use of visuals and the use of concrete. And the third one is a language. Those are the 3 things that has been found to be critical variables. It contributes a lot to subsequent level of learning. Any other question before we... Yes, please.
I totally appreciate that learning this rule of dividing with a fraction is like multiplying by the reciprocal it's far better that children begin to understand the underlying structure of the problem. However, when they are 3 years later, 4 years later, trying to simplify, they've got algebraic fractions and they're trying to simplify it, I do feel it's useful for them. Because when the situation is so different and it's so difficult to make it a concrete example, they have a rule in their head, okay, dividing by a fraction is the same as multiplying by the reciprocal.
And I say those are the top 3 things, but the next thing I would share with you is that when we do all these concrete things, it's for the purpose for us to generalize, to spot a pattern. Definitely. Definitely. I mean, that's what our human brain is for. We do things, we specialize to generalize. We do things on a daily basis, and over a period of time, we see similarities, we see structures, and then we generalize. And we no longer figure it out from the first principle. I think that applies across all areas of our life. So it is important. If I need to always start from the first principle, then I cannot go very far. Same for languages. Same for mathematics. So thanks for that. So you are right. Over time, you want them to spot a pattern. But it is the students who need to spot the pattern. Sometimes as a teacher, I'm too kind. I will tell them the pattern. Like, boys and girls, oh, that's something I noticed. And then we tell them. So when an adult tells children the rule, we are robbing them one opportunity to see a pattern and generalize for themselves. So I will just close with a story. So this story is something that we often read to our teachers and parents to help us understand a little bit about how we help young learners learn. I'll read to you the story. How to make sure the butterfly cannot fly. So if you want the butterfly not to be able to fly, this is the way to do it. How to make sure the butterfly cannot fly. How do you get the butterfly? First, there's the egg which hatches into a caterpillar. The caterpillar eats and grows. At the right time, it makes a cocoon out of its own body. While in the cocoon, the caterpillar changes into a butterfly. When the butterfly is ready, it starts to break through the cocoon. First, a hole appears. Then the butterfly struggles to come out through the hole. This can take a few hours. If you try to help the butterfly by cutting the cocoon, sure, the butterfly will come out easily, but it will never fly. Your help has destroyed the butterfly. Sometimes we see children struggle so much, and out of the kindness of our heart, we just tell them, and then they can do the procedure. So whenever we give them a shortcut, it's like cutting the cocoon. So are we willing to sacrifice the subsequent learning just for the sake of them being able to do whatever we want them to do? So if you want the butterfly to come out, if you want them to do that calculation quickly, that's an easy way. Cut the cocoon. Give them the procedures. Tell them the rule. They'll be able to replicate it. But our help has destroyed the butterfly. The butterfly will never be able to fly. The reason why, in the case of the butterfly, is that the butterfly can fly because it has to struggle to come out. That's just a natural way. The pushing forces lots of enzymes from the body to the wingtips. This strengthens the muscles and reduces the body weight. In this way, the butterfly will be able to fly the moment it comes out of the cocoon. Otherwise, it will simply fall to the ground, crawl around with a swollen body and shrunken wings, and soon die. Yeah, so that's a story that I share with colleagues. So thank you very much, parents.
Thank you so much for coming. Thank you, Ban Har. We're thrilled that he'll continue to work with elementary today and tomorrow, and our middle and upper school teachers actually on Thursday during the pre-conference. We're very excited because he provokes our thinking, and we continue to grow. We also welcome you to come to Another Edge. Next Thursday, we have Garfield Jenny Newman back this year. We really hope you come and hear his thinking about a thinking classroom. He's a great speaker and gives lots to think about as well. Ban Har can stay around for some informal questions for about 10, 15 maximum minutes, because then we need to get him back into classes. What's exciting is he's working with teachers. They're thinking about the lesson ahead of time. He's actually going in and modeling lessons, and then they debrief. So it's a very impactful approach that's being used with his time here. So thank you once again. Enjoy some more coffee and breakfast, and we'll hope to see you next week. Goodbye.